All right, today we've got Jesse's Girl by Rick Springfield. And we're taking a look today at stretching and reflecting the absolute value function. So quite a bit more difficult than translating. So a couple of things to keep in mind. When we stretch a graph, the slope of the sides will change. So remember when we looked at the parent function, the slope off to the right was +1, slope off to the left was -1. That will change when we stretch. A vertical stretch, when we write the equation, goes outside the asylum, and it is normal. Something happened with my formatting here. Let me see if I can move this real quick. There we go. All right, and with a horizontal stretch, that goes inside the asylum, and it's flipped. So you take the reciprocal of the stretch when you put it inside the asylum. So as opposed to opposites, when you translate, positive becomes negative. If you're stretching it horizontally by 2, you multiply by 1/2. A reflection, so when we flip the graph over the x or y axis, if it is an x-axis reflection, what I want you to think about is where those points land. So I'm going to make this really basic. Let's say we have a point here, and we want to flip it over the x-axis. The x value stays the same, the y value becomes negative or opposite. So that's why the negative sign goes outside the absolute value. And then a y-axis reflection, the x value becomes opposite. So we make the x inside the asylum negative. All right, so we're going to start with stretching. We're going to take a graph that's already been translated, and we're going to stretch it vertically. A stretch does not change the vertex, only a translation. So we can get the vertex of our graph from our new parent function, our x + 2, which would give us, remember we're in the asylum, so our vertex would be the opposite of what we think. And since we're not adding or subtracting anything on the outside, 0. So I'm going to go ahead and plot my vertex. And remember, what the stretching does is it changes the slope. So if you're stretching it vertically by 1/2, now instead of going up 1, you're going up 1/2. Or the slope becomes 1/2, which may be a little bit easier to think about. So I'm going to go up 1, right 2. And think about this as also up 1/2, right 1. We'll get the same slope. So just to make sure that we have that connection. And then, of course, off to the left, it will be a -1/2. All right, so stretching it by 1/2 is actually compressing it by a factor of 2, but it makes it a little bit challenging to think about because you have to do the reciprocal of the stretch when you talk about a compression. So I am just going to be talking about stretching. We're always stretching, and the factor is what will change. All right, so now we need to write our new equation. So again, I'm going to name it something other than our parent function. So I'm going to call it g of x for my transformation. It's vertically. Anything vertical goes outside the asylum, and it's normal. We stretched it by 1/2, so I'm multiplying by 1/2 outside my asylum. Next example we have here is we will write and graph the function that's been shifted down 5, and we will stretch it horizontally. Again, a stretch does not change the vertex, which makes this really a lot easier to figure out how to work with it. So I'm going to figure out my vertex. I'm not doing anything inside the absolute value with the x. Outside is normal, so I'm going to plot 0, -5. That's my vertex. And now the horizontal is opposite of what we think. So it says we're stretching horizontally by a factor of 2. So actually what this does to the slope is the vertical piece is normal, it's a 1, but the horizontal piece gets multiplied by 2. So up 1, right 2. And this might sound a little bit familiar, and it should. Up to the left, our slope is negative. So now we took the graph And think about how the parent function looked with that slope of 1. I'm going to kind of sketch that in here real quick. And think about taking the blue graph and pulling it off to the side. You are stretching it horizontally by a factor of 2. You're making it twice as wide. And thinking back to this last example here, when we stretched it vertically by a factor of 1/2, the same thing happened. We squashed it by a factor of 2 vertically versus stretching it horizontally by a factor of 2. I'm going to write this equation quick, then we'll be done with this part of the video. So when it is horizontal, it goes inside the asylum and it's not normal. So instead of a 2, it becomes a 1/2.